Right now, above your head, something older than mammals is crossing the inner solar system. Not a threat, not a mystery. A messenger carrying chemistry from another star. A team in Spain just rewound its path 10 million years through the galaxy. What they confirmed changes how we think about life's origins. This is what we found inside. July 1st, 2025. The ATLAS survey in Chile flags an object. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a NASA-funded network designed to catch objects that could threaten Earth. But this isn't a threat. Within days, the designation comes through 3I. The I stands for interstellar. Third confirmed visitor in human history. Not an ellipse bound to our Sunday, a hyperbola, one-way trajectory, foreign registry. This comet doesn't belong to our system. Never has, never will. The first interstellar object was Oumuamua, detected in 2017. It tumbled past too quickly, too faint for detailed study. The second was 2I, Borisov, in 2019, our first chance to properly analyze an interstellar comet's chemistry. Now we have number 3, and this time we have the tools, the time, and the trajectory data to decode what it's carrying. Researchers at the University of A Coruña in Spain took that trajectory and did something audacious. They fed it into Gaia, the European Space Agency's Galactic star map, measuring 1.8 billion stars with micro-arc-second precision, and ran the simulation backward, star by star, gravitational nudge by gravitational nudge, through stellar neighborhoods we've never visited. For 10 million years, let that number settle, 10 million years. 10 million years ago, our ancestors didn't exist. The genus Homo hadn't appeared yet. Continents were still shifting into their current positions. Ice ages came and went. Mountains rose and eroded. And this traveler was already moving, already carrying secrets from another star system, drifting through the galactic night. This is computational archaeology at the scale of the galaxy, and Spain's team pulled it off. But here's the critical window. Late October 2025, the comet reaches perihelion, closest approach to the Sun, at about 1.4 astronomical units. Then in mid-December, it passes Earth at approximately 270 million kilometers. That's about 1.88 astronomical units. Safe, bright, analyzable. No impact threat, no extinction event, no last night on Earth playlist needed. Just a cosmic lab sample drifting close enough for our instruments to harvest its secrets before it sails into the void forever. And every major telescope on Earth is watching, because opportunities like this don't come often. December 2025, the comet clears solar conjunction, that brief period when the Sun sits between Earth and the comet, blocking our view. Now the window opens. JWST's infrared eye locks on. So does the Very Large Telescope in Chile. ALMA, the Atacama Large Millimeter Array, joins in with its array of 66 radio dishes. The mission is urgent and singular. Read the molecule list. Decode the chemical fingerprint before the visitor fades beyond useful range. Why does this matter? Because unlike exoplanet transit spectroscopy, where we measure averaged atmospheric signals through thousands of kilometers of haze, a comet's coma gives us direct samples, ice sublimating in real time, chemistry frozen at the moment of formation, now boiling into space, where our instruments can read it molecule by molecule. This is forensic science on a stellar scale. Spectral lines reveal what's boiling off the comet's nucleus as sunlight warms it. Carbon dioxide, carbon monoxide, water, methanol, methane, hydrogen cyanide. These aren't random chemicals. They're the building blocks of prebiotic chemistry, the raw materials that lead to amino acids, sugars, nucleobases. The ingredients of life. Each molecule absorbs and emits light at specific wavelengths. We measure those wavelengths, match them to lab data, and reconstruct the inventory. It's detective work written in infrared and ultraviolet light. Now compare. On the left, 67P, Churyumov-Gerasimenko, the comet Rosetta, studied for years, even landing a probe on its surface, a typical solar system comet, water dominant. Carbon monoxide present but secondary, predictable ratios that match what we expect from our sun's protoplanetary disk. On the right, the visitor. The data comes in from JWST's MIRI and NIRSPEC instruments, and something's off. The comet runs hot on carbon dioxide, far more than water relative to our comets. The ratio doesn't match the solar system template. Preliminary analysis suggests the CO2 to water ratio is roughly 3 times higher than the solar system average. That's not a small deviation. That's a different recipe. Even 2I, Borisov, the previous interstellar comet from 2019, skewed closer to our baseline. It looked like it could have formed in a system similar to ours. This one diverges. What does that mean? Chemistry is written by environment. Temperature, pressure, radiation, the type of star, the distance from that star. All of these variables leave fingerprints in the ice. In our sun's protoplanetary disk, water ice dominated the outer regions beyond what we call the snow line. That's what our comets reflect. They're water-rich because they formed in a water-rich environment. But form a comet around a cooler star or farther out in a colder disk where temperatures drop even lower and carbon dioxide can condense before water does. The freezing point of CO2 is minus 78 degrees Celsius. Water freezes at 0. In colder regions, CO2 gets locked into ice first. Different temperature, different radiation field, different stellar wind, different recipe. This isn't our dialect, it's someone else's, and we're hearing it clearly for the first time. The researchers at A Coruña put it plainly. The composition tells us about formation conditions we can't replicate in our own backyard. This is comparative planetology at the molecular level. Now connect the molecules to what they do. Because this isn't just about cataloging chemicals. It's about understanding pathways, how simple molecules become complex ones, and how complex ones become the building blocks of biology. Ultraviolet light from stars strikes ice grains floating in protoplanetary disks. High-energy photons crack simple molecules. Water splits into hydrogen and hydroxyl radicals. Methane breaks into carbon and hydrogen fragments. Ammonia decomposes into nitrogen and hydrogen, and then the fragments recombine. Not randomly, chemistry has rules. Energetically favorable pathways. Surface catalysis on dust grains. Hydrogen cyanide, one of the molecules we detect in comets, is a gateway compound. In the presence of water and energy, HCN becomes formamide. Formamide, under the right conditions, becomes nucleobases, cytosine, adenine, guanine, uracil, the letters of RNA and DNA. Methanol and methane act as carbon reservoirs, feeding synthesis pathways we call Fischer-Tropsch chemistry, a process where carbon monoxide and hydrogen combine on metal surfaces to form hydrocarbons and alcohols. The same chemistry that powers some industrial fuel production happens naturally on interstellar dust grains. This isn't speculation. This is lab-verified science. Researchers have reproduced these reactions in vacuum chambers that simulate interstellar conditions, temperatures near absolute zero, UV radiation, cosmic rays, and they get the same products we find in meteorites and comets. And we found the products in our own comets. When Rosetta analyzed 67P over 2 years, it detected glycine, the simplest amino acid, directly in the comet's coma. It also found 16 different organic species, including formaldehyde, methanol, ethanol, and acetone. NASA's Stardust mission brought back interstellar dust particles captured in the tail of comet Wild 2. Lab analysis found amino acid precursors, the chemical scaffolding for biology. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids. Only 19 of them are found in Earth biology. The rest are extraterrestrial signatures, proof that organic synthesis happens in space. So here's the question the comet forces us to ask, and it's not a small one. If this visitor carries a comparable or even richer inventory of prebiotic molecules than our comets, what does that mean for the origin of life? It means panspermia graduates from wild hypothesis to testable framework. Not the old version, the one where bacteria or spores survive light years of radiation and cold. That's still implausible. But chemical panspermia? That's different. That's about ingredients, not organisms. Cometary infall during planetary formation. Micrometeorites raining down at thousands of tons per day on young Earth. Interstellar dust drifting through every star system, seeding every protoplanetary disk with the same basic chemistry. If chemistry converges across star systems, if every protoplanetary disk writes the same recipe into its ices, with only minor variations in the ratios, then Earth's prebiotic inventory was never unique. It was typical, standard issue, galactic boilerplate. And that changes the equation for life elsewhere. Because if the ingredients are universal, the question isn't whether life could start, it's whether it did. Step back, zoom out, see the bigger frame. 3 interstellar visitors in 8 years, 3 chemical snapshots, 3 time capsule spectrometers from different star nurseries, different formation environments, different corners of the galaxy. Oumuamua gave us almost nothing. It tumbled past too fast, too faint, and by the time we realized what it was, it had already left the observation window. We got trajectory data. We got arguments about whether it was a comet or an asteroid or something else entirely. But we didn't get chemistry. 2I. Borisov gave us chemistry. For the first time, we measured an interstellar comet's composition, and it looked familiar, close to solar system norms. Water dominant, Cn and C2 radicals matching our expectations. It could have formed in a system similar to ours. Now this comet shows us divergence. CO2, forward chemistry, different ratios, a distinct signature. And that divergence is the data point we needed. Because if every interstellar object looked identical to ours, we'd learn nothing. And if every object looked completely alien, we'd learn nothing. But variation within boundaries, that tells us something profound. It proves that chemistry varies temperature, stellar type, disk composition, all matter but within constraints. CO2, rich, water-rich, methanol forward, HCN heavy, different accents, same language. Because all of it starts the same way. Cold molecular clouds, hydrogen, carbon, oxygen, nitrogen, the 4 most abundant reactive elements in the universe. Gravity collapses the cloud. A star ignites at the center. And chemistry begins. UV radiation from the young star, temperature gradients across the disk, stellar wind stripping volatiles from the inner regions, dust, grain surface chemistry in the cold outer zones. Those variables tweak the ratios, shift the abundances, write different dialects into the ice. But the core ingredients, universal, written into the periodic table, baked into the physics of star formation, which means our origin story was never strictly local. The chemistry that made Earth habitable, the organic molecules delivered by comets and asteroids during the late heavy bombardment, wasn't unique to our system. The recipe for life might be galactic standard, written into cold molecular clouds long before stars ignite. And every system that forms around red dwarfs, sun-like stars, blue giants in their brief lifetimes starts with the same pantry. The ratios differ. the abundances shift, but the menu is the same. 4 billion years ago, Earth was bombarded. The late heavy bombardment delivered trillions of kilograms of material to the young planet's surface: comets, asteroids, dust. Some of it came from our own Oort cloud and Kuiper belt leftovers from the solar system's formation, but some of it, maybe a lot of it, came from out there. Interstellar dust drifting through the disk, rogue comets captured during the sun's birth cluster phase when stars form close together. If that material carried the same prebiotic molecules we're finding in this visitor, if Earth's organic inventory was seeded partly by interstellar chemistry, then life didn't need a miracle. It needed chemistry, water, energy, and time. 4 billion years is a lot of time. This comet isn't an omen. It's a control group, a reference sample, a way to test whether the chemistry we see on Earth is typical or exceptional. And if it's typical, the implications ripple outward. The spectra are still coming in. JWST, VLT, ALMA, every instrument is recording. Over the next weeks and months, astronomers will refine the ratios, confirm the organics, cross-check against our comets and 2I Borisov. They'll look for isotope ratios, deuterium to hydrogen, carbon-13 to carbon-12 signatures that reveal formation, temperature, and stellar environment. They'll search for complex organics beyond the simple molecules we've already detected: formaldehyde, acetylene, ethane, maybe even amino acids, if the sensitivity is high enough. If the preliminary findings hold, if the CO2 dominance is real, if the organic inventory matches or exceeds expectations, we'll have proof that life's building blocks aren't rare. They aren't special. They aren't a fluke of our particular star or our particular disk. They're everywhere. Every star, every protoplanetary disk, every ice grain drifting through the dark, carrying the same chemical seed. Think about what that means. Right now, there are trillions of comets drifting through the galaxy, ejected from young star systems, wandering the space between stars, carrying chemistry. Some will be captured by other systems. Some will collide with planets. Some will seed worlds we'll never see. And if the chemistry is universal, every one of those worlds starts with the same toolkit. So here's the question the comet leaves us with, and it's one we'll be asking for generations. What changes if every system starts with the same ingredients? Does life become inevitable given enough time and the right conditions? Or do other bottlenecks, energy sources, stable climates, planetary protection from radiation matter more than chemistry? We don't know yet, but now we have a way to find out. Every interstellar object that crosses our path is a data point. Every spectrum is a vote. Every molecule is a clue. Watch the spectra with us. If these ratios hold, we're not just studying one comet. We're reading the Galactic recipe book. And every page says the same thing. The ingredients are universal. What we do with that knowledge, how we search, what we expect to find, how we think about our place in the cosmos, that's the next chapter. And it's already being written.